Hey guys, today we'll be doing a tutorial on a honeycomb lattice compression on Abaqus. So before we start, let's look into what the project is going to be like. The first thing is, of course, we'll be having a line, and then we'll be having a honeycomb lattice. Is there a hexagon there? Yes. So we have multiple honeycomb lattices, and that's the big picture. And they all align up properly, and they form a lattice, which will be used for compression. And the goal is that this plate right here will be subjected to a load, and it's going to compress it downwards, and we'll be seeing the effects on the honeycomb lattice. So to start with that, let's hop on to Abaqus. Now Abaqus by itself doesn't have any units, and which is quite confusing for a lot of people at first, but what you need to know is that the units you're going to use will be based on a system, which can be anything of your choice, and you must stick to that system no matter what you do. So the first thing in Abaqus is to see what the layout is like. As you see, here is the basic toolbar. Here is where you get the model toolbar as well, and here I'm not really sure what to call this, but we just call this the mini toolbar with the icons. And up on here is a tool for you to select the different parts of the Abaqus simulation, which we'll be using a lot more often. So we'll be looking into that first. The first thing to do is to hop onto part. This is basically you creating the sketch for the honeycomb, and to create a part, press on this icon here. As you can see, it shows up a dialog box saying create part. So click on it and name the part as honeycomb lattice, or let's say honeycomb ls lattice base. And you see a bunch of options. The first thing is the modeling space. Since we'll be performing a 2D compression, we'll be looking into 2D planar, and the next important thing is to choose the type. Now we have three types: deformable, discrete rigid, and analytical rigid. We know that lattice is going to get deformed in some point in time, so we'll be choosing deformable, and the base feature is a wire. Now here you see something called approximate size. This is basically the dimensions of your sketch pad. For now, let's stick to 200. So how do you create a hexagon? Well, there are multiple ways, but a way that I like is by creating a circle first. You can see the mini toolbar has a bunch of things. So in the first column, second row, you see something called create circle. So you hop into the origin. You can see from the dotted line intersection point, and you draw a circle for 10 units. You see what I did there? I said 10 units, and I did not say 10 centimeters or 10 meters, because right now, let's just draw the circles. So after that, I want you to create a long line. I like calling it long line. Just click on any random point and create two lines of sort. Now create two more lines from this side. It can be of any arbitrary angle. For now, let's just create them. Then after that, hop onto the add dimension icon here. Click on this line and click on this line, and then just choose any random point and click on it. Doesn't really matter, and type in 30 degrees. Now you can see here that there's a prompt which asks me for what dimension I should enter. Now we'll be doing a lot of operations here, so make sure you know this exists. So press 30 here. Now repeat the same steps for the other lines. The same thing here, and the same thing here. Now once that's done, hop onto the mini toolbar again. Now choose the second column first row option called create lines. Create the hexagon. Now it is important that we're doing a hexagon that is in the zigzag orientation instead of armchair orientation. So once that's created, press escape to end the operation. Now we have to delete all these lines. But before that, let's just make sure that our sides are exactly 10 units. As you can see, it says 10 units, so I think we are in the good. Of course, there are some lines here. For example, this lantern line is not exactly 10 units, but it's approximately that. And to show you guys exactly what to talk about it, as you can see here in the prompt, you see it's 10.00000, and there's it doesn't end off as a whole number, so just be aware of that. Now because of that rounding error, we can't really use a linear array pattern creation to replicate the design. So instead we'll be sticking to the good old method of copy pasting things. So let's delete these construction lines by using this very apt eraser head icon here. You can just create a box to select multiple things and press enter, and let's delete the circle as well and this line as well. So now we just have a hexagon here. But now how do we make a lattice out of this hexagon? Well, the first step is to create our extension points. This allows us to replicate this much easier, and that is something we need. And let's delete this line. I'll tell you exactly why this is important, but for now, let's do that. So next thing I want to do is to translate or just copy this sketch onto this side in the x-axis. So to do that, hop onto this thing called translate, and as you see the prompt asks us what kind of operation we need. Let's say copy. We press copy. Now it says select the entities to translate, so we select the entities, we press done, and now it asks us to pick a starting point for the translation vector. So let's choose this point and translate to this point. So now you have this beautiful shape here, and let's repeat the same action again. And for now, I'll make a very simple lattice since I don't want to waste any time creating this. And let's connect this point as well. Now to make it go upwards, to copy it upwards, perform the same step, press copy again, select the entities, press done. Now from this side to this side, you have a vector here. And that's beautiful, isn't it? And as you can see, there's a line here and there's a line here. We have two lines being connected. Now just to make it look nicer, let's just select these points and delete them and create this with a single line. So press delete. Of course, you could always copy the line that I just made and use the linear array pattern there, but I like doing things old-fashioned. So after that's done, you might recall that I deleted this member of the hexagon, and that is because if I copy pasted the entire element again, there would be an overlap at this very specific member, and as I copied these two hexagons to this side, the copied member here, the one that's been affected twice, will spread itself, and that is not something we need because we could fix it by deleting those members, but we could avoid that mess entirely by just doing it from the very beginning. So before we exit, let's make one small measurement, and that is the measurement of our base plate. And now our base plate must be bigger than the hexagon. So this is around 70 units. So that's something to keep in mind of, and that's pretty much done. So we made the hexagon, looks beautiful. But now what about the base plate? So we'll create another part, click on this, name this as plate for now. Sorry, can't type. It's a 2D planars thing, exactly like a lattice. And is it deformable? Well, no, it's not deformable. It is discrete rigid. It is a wire point, and it's good. So let's make the sketch again. Now remember how the length of the entire hexagon array was around 70 units? So let's make this a bit above 70, and let's just go with 100 because why not? It's a good old number. So from -50 to +50, and press enter. Sorry, and that's it. So let's finish the sketch, and we have this cool little line here. Now, how do we attach this line to our hexagon? To do that, we need a specific point of contact, or a representative point, or a reference point. To do that, go to Tools, click on Reference Point, and you see all these little nodes light up. Click on the center one, and that's it. We've just created a reference point. Now, luckily for Abaqus, luckily for us, Abaqus has a streamlined option of creating our simulation properties, simulation jobs. So let's click on Property here, and this is where we assign all the properties. Go back to Honeycomb LS by clicking on the Part dialog box here. Click on the first option called Create Material. Let's try to model for aluminium because aluminium is a nice material. And click on Mechanical, click on Elasticity, and click on Elastic. Now, as you can see here, we have the type to be isotropic or orthotropic or anisotropic. For now, let's go with isotropic. Temperature dependent data, no. Compression, no. No tension, no. Let's send the Young's modulus to some number. But what exactly should this number be? Well, remember how I said Abaqus has no units? Well, we will be invoking the units right now, and the units that we use right now will determine the units we'll be using for later things. So let's stick to the basic good old SI unit system for meters. And since the Young's modulus of aluminium is 70 GPa, let's just write, for a more accurate response, let's write 6.8 E10, and the Poisson ratio is around 0.3, so that's good enough. So that's done, but how do we assign the material to the hexagon? Well, it doesn't automatically do that, so we have to press this button here called Create Section. What does the section do? Well, it tells us that this wire element has some sort of section to it. So the kind of section we are going for is for a beam. And let's name this a beam section. And we'll be choosing a beam as a type. Now, what is the difference between a beam and a truss? Well, a beam experiences bending while a truss doesn't. That is pretty much the gist of what it means. So let's go with the beam. So click on beam, and you can see a bunch of things here. Let's worry about the profile name. To do that, well, there's nothing here. Well, click on this icon you see over here and type circular profile as the name because you'll be going for a circular profile here. Click on circular and press continue. Now you can find the radius here. I'm going to set it on 0.1 because it's a very small radius, and that's it. Stiffness, fluid inertia, no, you don't have to worry about that. But the section Poisson ratio, well, let's set it to 0.3, and that's it. The next thing is assign section. Do we need to create a set here? A set is basically a group of elements or a group of nodes which we could further use to perform calculations on. But for now, we don't need a set, so let's keep it as this. It's just a placeholder. And let's select the sections to be assigned. Create a box, press done. Beam section, yes, it's aluminium, yes, cool. Now press on this command for beam orientation and press done. And press enter and press OK. So now that we assigned the beam properties and the beam orientation, let's go back to assembly to assemble our hexagon lattice. Click on create instance on the mini toolbar here. Click on honeycomb lattice. Click on plate. Click on honeycomb lattice, press apply. Now you can see it came here, and press plate and apply, and that's it. So now how do you attach this plate here and here? For now, let's attach the plate here. So click on this point, click on this thing called translate instance, select this instant here, click done, select an access point, click on this reference point here, select an endpoint. Well, If I made a 5 hexagon lattice, I would ideally have this single node here, but for now let's just click any of the points here because it doesn't really matter. I mean, it kind of does matter, but it's fine. So we have this, and we'll say okay. So now let's create another instance. This is for the top plate. Click on the plate again and press apply and cancel. Now translate this point again, select the instance, press this, click select, and press this point, and that's it. So now we attach the top plate and the bottom plate, and that's pretty much it. Wow, I just cancelled that. Let's speed on this. Done. Okay, we just finished the assembly. And now let's go back to step. Well, for now, let's skip step and go back to interaction. This basically tells what's happening with the reference point and the lattice nodes. So click on create interaction. Click on top interaction. Press surface contact standard. Press continue. Select the main surface. This will be our main surface. Done. Choose a side for the edges. Let's go with the yellow point. But choose the secondary type. Let's go with node region. Select the points for secondary nodes. Select these points here. And by using control, deselect these points by pressing control. You could of course draw a box here and press on RP as well, and press and click enter, and that finishes it. Now for the top interaction, we have this dialog box open here, and contact interaction property. Well, we have nothing here, so click on this and click interaction property, press contact, and done. Mechanical, normal behavior, hard contact, yes. Okay, and press OK here. And do this exact same step for here as well. So click on create interaction, bottom interaction, main surface. Click magenta here because that's something we need to do. Press node region, select the points with secondary, same thing here, same thing here, same thing here. And remember to click off RP as well. And that's pretty much it. Choose the interaction property and done. It's the same thing as before. So now we finished the interactions. Let's go with the next step of creating loads. Now the load that we're applying here will be a displacement load on RP, and the bottom point basically has to be still, as in there will be no displacement from the bottom because it's kind of fixed, right? So click on this, create load, but you can see something here. There are no analysis steps in the current module. Loads may only create an analysis step. So to do that, let's create a set here first. Tools, and set, create. Let's call this top RP. Click done. Same thing again, set, create, bottom RP. Done. And now we finished that. Let's try doing the loading thing again. Well, same issue. Sorry, never mind. So you go to the next thing, you mesh it. So let's mesh it by part. Click on the part here, go to the honeycomb lattice structure, select the entity, press seed edges. We'll be meshing by size for now. Hopefully it works out. Remember, in Abaqus student version, you have a mesh limit of 1000 nodes. So just keep that in mind when you're meshing. So press apply, click OK. Now press mesh part, click yes. And as you can see in the window here, it shows 500 elements have been generated, which is well below 1,000, so it'll be fine for now. Do the same thing for the plate. Select, seed edges, apply, okay, mesh the part, yes. So we have 100 elements on this, which is a lot of elements. It's not really required, but it's fine. So because we'll be using two plates, we'll be having 100 nodes, 100 elements, plus 100 elements, plus 500 elements on the lattice structure. So all in all, we will have about 700 node elements. So it's fine. It's well below the 1,000 limit, and it should work. So let's go with the step part again. Let's say it's create a step. Let's call the step 1. It's the step after the initial step. And what exactly are steps, by the way? Well, think of the first step as the initial point of anything, and the next step to be all the time after the first point. This is basically telling us how the model will react after the first initial conditions. So we create this initial point, initial step, and let's call the static general, and press continue. Description, you could add one if you want, but it's fine. This is the incrementation part. Let's see the increment minimum to be 0.1, 0.01, maximum to be 0.01. Okay. Now after that, go to the load condition. Click on select load. Let's call this top load. This is a concentrated force. So press on continue. Click on this point and press done. Well, that's a mistake. You shouldn't do that because you're concentrating a point here. That's not something that we need. Because we need to compress this entirely, we need to have a uniform compressing force here, which could be achieved by this thing, causing a boundary condition. Let's call this dot BC, press symmetry, displacement, click on this point, and that's it. And let's select U1, U2, U3. Let's set this as 0.20. We'll be doing a displacement of 20 meters. Do the same thing here. We'll be doing a displacement one as well. Let's call this bottom BC. Continue, press this point, RP, and done. Now this is an Lancaster condition, so we could set everything to 0. Or we could just do it here itself. You can see Lancaster here. Press on that. BC, RP, and done. Lancaster 0, and that's it. So now that we finished the loading, everything is done. Optimization, it's fine. But let's move on to the job part. Go to job, press create job. You can name this tutorial or something if you're liking. Press continue. It's fine. Let's go to jobs here on the model toolbar. Press submit. It's running. That's good. Okay, it's done. Press on results. Now this is our initial point. Click on this thing here, and that's the deformed shape of it, which looks nice. And this is the contour for the deformed shape. S is the stress here. We could change the contour by going here on top selecting displacement u or epsilon for strain. Now you can also see an animation of this by clicking here, animate time history. Now as you can see how it's getting deformed. We could slow the animation down by pressing on this icon here, right below the animation option, and you can reduce the amount of frame rate it shows. Click apply, and you can see it slows down considerably, so we can exactly see what's happening to the shape. And that's it. Now to get the data from this, let's go on to history output requests, press on this, press on output 1. You can edit this, press on this. You can edit or create, and let's go with edit because why not. Uncheck energy, click on set, and remember the set we defined, that's the bottom RP, and we want to find out the displacement and the force on this. Open up displacement, open up U2 because that's responsible for the y-axis displacement. Forces RF2 again, and press OK. And do the exact same thing. Press on history output request, press create, step 1, yes. Whole model, no. You go for set, top RP, displacement, U2, forces RF2. Sorry, I forgot to press stop RP here, and that's it. So now we created the history output request. Run the exact same job again, press submit, let it overwrite, it's fine. Now let's see the results. Same old, same old. So now let's create a plot. Click on ODB history output. Press on this. Now press plot, and you can see it linearly increasing. Of course, displacement. So now how do we combine those plots of displacement and force? To do that, press on this, operate on X and Y data, and we can use commands here to do that, but for first we need something in the XY data point. So to do that, let's save some data, press on this again, go to ODB history output, press continue. Now we need the reaction force from the bottom node and the displacement from the top node. So the reaction force from the bottom node is the first one. So let's say save as is, let's say force, and we need the displacement from the top node. So that's the top reference point. Press on this again, press save as, and display displacement. I'll say display for now, and press OK. Now close this, open up XY data again, operate on XY data, press and as you can see here, there's this other box here. Press on combine, there should be combine here somehow, yes. And displacement, double click there, double click force again, create XY data, sorry my bad, plot expression, that's the term. Now the XY data has been created, and as you can see there's a force axis here and a displacement axis here, and this verifies the result because of force over by 3 creates a displacement of 2.0. Now what is this 3? Well, it's 3 to the power 10 to the power 6, 3 to the power 6 newtons, because we use the metric system with meters, SI units. And that's pretty much how you make a plot. Now you could then export this plot by using something called plugins. Go into toolboxes, I meant to say tools. Go to Excel utilities, and once you press on this, you can choose the plot you want to show, which is the current XY plot. Then you could press OK and apply, and you can get onto Excel and it will plot for you as well. And that's how you can manipulate, not manipulate, that's how you can exactly see what values are being used. And that's pretty much it. on the tutorial Abaqus. But before you end here, I do want to show you a very important thing. Remember how the boundary conditions are defined? Well, we have the top boundary condition, and let's go back to and edit this. Now it is very important that you select u1 to be 0 and r3 to be 0, because in cases where you don't do this, what ends up happening is the plate here ends up sliding in one direction. I'm not too sure why that happens, but by restricting the motion of the degrees of freedom, we can constrict Abaqus to only go downwards, and that is something that we desperately need. And that's pretty much this tutorial. And yeah, it's very cool software. I personally want to use it a lot more, and yeah, that's pretty much it.